So I'll be talking about some recent work. Let me just make sure that this is the this one. Okay, that's perfect. It's some recent work aimed at understanding the magnetar phenomenology, as well as some ideas on the possible use of highly magnetized neutron stars for cosmological purposes. So just a very brief introduction, although it's not needed, but just to put everything in context. Neutron stars are one of the two remnants of the end state of massive stars, and in particular, they are from stars up in a range of masses between something around 9 and 10 and 25 or so solar masses, with a fraction which depends on metallicity. Then just if we consider all the so if we combine how many neutron stars are born for a given IMF, what we find is that the number of neutron stars to black hole actually is it's a fraction roughly 10 to 1 higher. So neutron stars are the most common end state of a massive stars. And if one combines, these results on the fraction of stars that become neutron stars with all the stars that were born and died within the Milky Way alone, one would find a number of neutron stars somewhere on the order 100 million to 1 billion of neutron stars. There is many of those, but just the sheer number is not why these are interesting. Neutron stars are places where both general relativity and quantum mechanics are at work. So they're extremely interesting places for studying physics. And with that, so it's a combination. I mean, even just how many stars were born in the entire Milky Way alone. It's just absolutely. So this is a total, because once they're born, they stay there forever. I think it's in the history of the Milky Way that comes into that. Also the IMF. So these numbers are from Hager et al. And this is different IMF. So even just that. So they have different precision here, and you see just the ratio that. So it's a factor of few coming from that alone. Probably the part that's best understood is the mass range where there is a separation between neutron star black hole. That's the one which has least uncertainty. Anyway, that was just a very brief review with on neutron stars. Okay, so now talking in particular about these special objects that I'll be discussing later more theoretically. So I'll start by describing what their properties are, how they were classified observationally, and then what we know, what we understand now theoretically. So in this zoo of many isolated neutron stars, the ones that I'll be discussing, so they were originally classified, so I'll talk historically, as anomalous X-ray pulsars, or in short for AXPs for now and the following, and soft gamma repeaters, or SGRs, in the following. So this summarizes their property. Periods which are rather long. So periods are tenths of seconds, and this is just to contrast with with the most of the other pulsars that we know that are more in the millisecond range. Rather steady spin down luminosities, which are rather high, and we'll see particularly what the high means. But just to give you some number on the order 10 to 34, up to even as close as 10 to 36 erg per second. Ages, rather young, 10 to the 3, 10 to the 4, most of them, a few on the order 10 to the 5 years. And no companion to accrete from, which is something that is also crucial as we will see. Now, in addition to this, so these are quiescent properties as they were originally discovered in this is a lot of discoveries were in the 90s, early 2000s. It's still relatively recent field. So in addition to those quiescent properties, also these AXPs and SGRs had some peculiar properties, and they were that every so often they were yielding outbursts. So these outbursts were distinguished observationally again. In some they were small and short, and others that were longer that I'll show in a second. So these are example of the small ones. Again, it just as observation were a bunch of different ones from different observation. It's something that to notice that these small ones were exhibited by both the HSPs and SGRs. So here I just picked a random collection from both classes. Short durations, fraction of a second, and luminosities as high as 10 to the 41 erg per second. Frequency, very variable from object to object, from weeks to years. So this, again, were classified in the early 2000s as objects were being discovered. Now, in addition to the small burst, what made the SGR be called SGR historically was the fact that they were observed, that's how they were actually discovered originally, which gave their name, by the fact they were yielding occasionally, so very low frequency, more of tens of years, a giant flare. So this is the soft gamma ray, soft as opposed to harder, which was characterized as the gamma ray burst. This is an example here. It's a very famous one. It's, as you see, lasts a little longer than the small burst shown before. It was displayed only by the SGR, again, historically, as they were discovered. Peak luminosity on the order 10 to the 44, 10 to the 45 erg per second. And if you couple the luminosity with, if you look at how they last, so 10, few hundreds of seconds, then it's immediately easy to gather from here that in a single event, as much as 10 to the 46 erg of energy could be released. So it's a huge release of energy in just a single event. The period is the period. So they're rather steady spin down. Occasionally they also have had glitches, but that's but it's they're really in fact it's so rather steady spin down as I. Absolutely. So this may burst again, but the frequencies, however, tens of years. So I'll get to that later. Yeah. Sorry. Oh, why it started 50? I think so. There is a trigger on when. So here, t equals 0 is probably when they started to get above the background. I'm guessing, and then they started monitoring, and it went into outburst. So they have been, I think, they have been monitored for. These are just a sky survey. So the question, which has been long-standing in this area, is what provided the energy source. And again, I'll give you a little bit of history before we get to where we are now. So natural candidates. This is first one is rotational energy, which is the most natural candidate for the most pulsars that we know and love. There is a correlation between X-ray luminosity and E dot. The X-ray luminosity is a small fraction of E dot, and actually there is quite a correlation over many orders of magnitude, which makes you believe that rotational energy is indeed the source of energy for the luminosity for many of them. However, if you look at these objects and this specular object that I just described, the opposite relation holds. So in the normal pulsars, this is much larger, and there is a correlation. It's like 0.1%, the slope of the curve, roughly. Here, it's the opposite. These have very long periods, which makes E dot to be very small. So rotational energy is completely out. That was clear from the very beginning. Accretion from a companion. This was the one natural explanation, because we know that X-ray binaries have luminosity size 10 to 36, and why not? This could be just standard X-ray binaries where accretion from a companion will produce those luminosities, no problem. So companions were looked for. This was done in the early years, because again, it was a very natural explanation. However, down to very tight limits, there is no companion. So these objects are isolated. And then there's been another model, which has been another idea that has been, it's been discussed for many years. And the idea is that, okay, you don't have a companion, but accretion is still a very good source of energy. So how about accretion from a fallback disk? We know that, when stars collapse, stars are rotating. So if the material outside of the neutron star has enough rotation, enough angular momentum to form a disk, then the disk can accrete for a certain number of years. And models were built that showed that actually you can devise a typical fallback disk they can contribute, can accrete on the neutron star and make it shiny for 10 to the 4, 10 to the 5 years. So this model I put like because it kind of summarizes what is the current status of event. There are still papers being written on this, so that's why I don't want to kill it. So the bottom line is they can explain the quiescent luminosity if you start with the, you build yourself the right initial condition for the disk. There's never been a satisfactory model for the outbursts, so they always have to make up some other story for how to have these giant flares, because from just a quiet accreting disk, you will not produce these giant flares that we saw. So and then having a hybrid model, it's much less satisfactory. Anyway, but there's still there have been still occasional papers on this. So what we believe now, and will be I'll be continuing on with these ideas, is that magnetic energy is believed to be the culprit for these properties. So let me start by none of the magnetars and binaries as far as we know. So there is companion and be looked in all of them. There is no evidence for a companion. So to the tightest limits that people have taken. So that's which is exactly why he became an all. So I'll continue with that. And so first with the order of magnitude, estimates and why magnetic energy can reproduce these properties, and then I'll go more into details of understanding more the detailed properties of these objects. So first of all, just the first thing, is there enough energy? That's the first question that one may wonder. And we see here, if one places a few times 10 to the 15 Gauss in a neutron star, then there is enough energy to power an outburst. Remember a giant flare that was, if you remember when I pointed out the attention to the soft gamma repeaters, where in one single event you have 10 to the 46 erg, so you have to have that. And hopefully you don't want to get rid of all the energy at once, because there would be a lot of it in a single event. So if you can have enough energy that a fraction of that it's being taken by the event, that's that's what you need. So there is enough energy if you allow yourself for sufficiently high magnetic fields. The idea behind the possibility of magnetic fields plays such an important role in neutron stars, where when go all the back to Thomson and Duncan, so they have a lot of credit. They also coined the term magnetar. And the idea is that outbursts were produced when magnetic stresses in the neutron star are strong enough to exceed the breaking stress of the crust. So this is the basic idea that they put forward, and then in their work. And something I want to mention, because I'll be following most of the ideas from Thomson Duncan in the following. However, there have been recent idea which suggests that maybe events can start entirely in the magnetosphere of the neutron star without involving the crust. Oh, I misspelled it. Sorry, Magnetos. Okay, this I had it last night, and you can see I was tired after 4 hours of training. Try this. Magnetos. Yeah, this is like I had it like because I wanted to mention also other ideas, and it was for. Right. So the idea, there is both of them that they have very strong magnetic fields, but here the idea is that you have, in these models, there may be twists that then reconnection events, and you have a bigger volume also. But as far as these are ideas, there's been no, there's been modeling of single events, but there's nothing on the statistics and also what in combination with the luminosity, which is what we've been doing with the more crustal model. But I wanted to mention, except 4 hours of training, that's what they do to you after. Anyway, magnetoscope. Oh, here. Okay, so then I have to go. Right. Oh, thank you very much. All right. Okay. So I'll start by just showing some older calculation by these are Jeremy Heil and collaborators. Just to give an idea, and then just for historical reasons, since they were doing these things, early on. So what basically, so I discussed that there's enough energy for the outburst, so that's one thing to which we'll come back. And then there was the other piece of the story, which is having high enough luminosity to remember that they cannot be reproduced by the E dot, as I was discussing before. That's the other properties of these peculiar classes of sources. So what they show here, simply by running very simple thermal models with thermal evolution models with various magnetic field strengths, basically that the temperature, which is plotted here, the temperature grows with it's higher for the stronger the field. So basically, the bottom line is that once you're below a certain field, which is somewhere around 10 to 12 or so, then either you have B equals 0, you have B equal 10 to 12. It basically, magnetic field doesn't affect the thermal evolution of the star, because the thermal evolution is determined by the star being very hot at the beginning. So you have to exceed a certain amount, a certain strength of magnetic field until you get to a point that the magnetic field does affect the thermal evolution. So the whole point of that here that they show is basically once you are in the range of 10 to the 14 or so, then you exceed that, and then the magnetic field becomes important in the thermal history of the star. And also the other point here to notice is that, again, if you integrate the whole energy that's been released over the number of years that 10 to 5, 10 to 6 integrated over here, you have enough energy, so you get something on the order 10 to the 48 ergs or so released over the whole lifetime of the star, which is, again, if you remember a few slides back, it's as much energy. The star will have a magnetic field for an internal field of a few times 10 to the 15 Gauss. So bottom line, there is enough energy both to power this enhanced extra luminosity that are seen for 10 to the 5 years or so, as those objects are seen, as well as to power this very luminous burst, especially the soft gamma repeaters. Oh, no, sorry? Neutrino cooling? Yeah. Oh, yeah. So right. So these are the earlier work by Hale and Kulkarni was a very simple, exactly. But the term, but that is, I mean, those are cooling curves. So maybe I misunderstood the question. Oh, from the bottom, but that's right. So in the more modern cooling curves, both are included. So so the cooling curves have both the neutrino component. So without magnetic fields, you have the normal cooling curves, and then there is the addition of magnetic fields. So they do include neutrino cooling, like the Urka process. The effect of the back reaction. I don't think so. Yeah. So going back. Okay. So going back to the. Now, to put this in all together in context, so the question is, so we discussed from independent evidence that magnetic energy plays a role in extra luminosity and in the outburst. And now we also the point is that we also have an independent way to estimate magnetic fields, which has been the standard way in the literature for a historical way, and it is. Based on the fact that neutron stars are known to primarily slow down by dipole radiation emission, and therefore simple relations, model some factors here with of a few allow to measure from P and P dot, period and period derivative, the dipolar component of the magnetic field. So if one puts these objects which had these peculiar properties on luminosity and outburst on this PP dot diagram, it's all consistent. They do occupy a region which is separated, and this is the direction of high magnetic field. So it's consistent with the region of high B field. So there was a point where everything started to come together, and okay, so everything started to come together. So this is a time where we started to work more quantitatively on this object. So first of all, I'll start by describing some general theoretical work, and then with application to these objects, and then coming to some puzzles that were produced, that were the result of more recent observations. So first of all, as one wants to simulate the evolution of this highly magnetized neutron stars. So what one needs is a coupled thermal, a magnetic evolutionary code. So this is work that a group in particular Pons and collaborators developed over a number of years. And I'm sure I don't have to remind you, the coupling is simply the magnetic fields that produce gel heating. Therefore, B evolution influences the thermal evolution. And then thermal evolution affects the conductivity and induction equation. Therefore, the two are coupled together, obviously. So I will, something I want to point out though, that as far as this, so this has been an area that's been growing, and for many years, there were the cooling codes without magnetic fields, and then there was magnetic fields, but it was not fully coupled to the temperature. And also, up to this work where Daniele Vigano, students of Pons, the old thermal was not fully included. So there were some, so numerically, they were included, but it was doing, so it was not fully consistent without going into detail. So this is the first time that finally the thermal and magnetic coupling has been done fully consistent, and it's the only code in the literature now that does that. So these are some sample simulations, because then we'll go, as we discussed, of actual objects, actual applications. So these are, as the magnetic field evolves, so magnetic field evolution, thermal evolution couple. These are for just sample initial configurations, so modeled, well, whatever, named with some letters. And basically, the difference is here. In some models, it's mostly crustal. The field is concentrated in the crust, so there are different intensities of the poloidal component field. And one case is also a stronger toroidal field, this one AT, which is the red one here. So something to notice now, because it will come back later, that if there is a toroidal field here, then the evolution is much faster. But as it evolves faster, correspondingly, it produces higher thermal luminosity. So something that will come back later, and it's again natural. So if you have a stronger field, you have stronger dissipation, will decay faster. So it's well, numerical result, but it's also intuitive. If the field is concentrated in the core, for example, this is another example here. There is very little evolution of the field, and correspondingly, there is not much enhancement into luminosity. Yeah. Exactly. So basically, the configuration of the field, exactly. So it's the configuration that the star would presumably have once it freezes. So it goes through this very, initial phase where it's malleable and the field evolves to some dynamo. So this is something that's not simulated here. So the way, what our work is, okay, assuming that this is the initial configuration, how does the field evolve, and more importantly, how, that evolution compares then to what we see. It is some I mean, this evolves under, because of atomic dissipation will make it evolve naturally, and then the whole term. So those, even if it's not an equilibrium, because it's dissipating, as it dissipates, it changes the configuration, so we'll go out of equilibrium. Right. So this is in the crust. Although we consider one case also in the core, but the core is also less understood as far as exactly. So there is assumed like superconductive and not much dissipation. So with that in mind, just what we did was compare. So first of all, there was a lot of work here in this same paper that this student, really good student, did. Also, so we compiled all the isolated neutron star, all the isolated, so not only magnetars, but every single neutron star for which there was X-ray data in the literature, and to have, because different people had the different methods of analysis and different instruments, so he reanalyzed everything, so that was done with one way, so that all the X-ray luminosity, all the temperature were calculated in the same way. So this is also, it was a big effort of just doing that part. And then, so what you see here in different colors are all the various subclasses that observers have named depending on their observational characteristics. So there is, X-ray dim isolated neutron stars, radio pulsar, and et cetera, et cetera. They come in different colors. So these are all the ones that have X-ray observation that had up to last year. And the magnetars in particular are the ones in red. So what we did here was basically comparing. This is the bulk of the population, so not tailored to any specific object, but simply comparing tracks in periods with magnetic, with the full magnetic field decay, and corresponding what they correspond in terms of thermal luminosity. So something I want to point the attention to, because it's an obvious point, but it turned out to be very important. So if there is no magnetic field decay, so if magnetic field decay does not play a role, then these are the tracks, the B-field tracks. So these are these parallel lines, and this is on the PP dot diagram, the pure derivative. So if there is no B-field decay, it's a very analytical, simple relation, and it just goes here. However, so if that was the case, we would have to have many objects, because these are also older, but this should still be observed, that periods 20, 30, 40 seconds. So there is no reason why we have quite a few objects clustered around 10, 12, but then nothing at 12, 20, 30, 40. Nothing observationally prevents us to detect a period at 10, but not at 30. And there should be even more of those. So okay. So these models here follow evolution in the crust. So what happens in the magnetosphere, it's not followed. So if there is reconnection that may affect a bit, may momentarily cause a glitch, for example. So that's an old separate. But this is like the long-term evolution, so averaged out basically over such disturbances due to magnetospheric events. But it's a very important point that I want to come across here, make across here. The fact that if there was no magnetic field decay, because this by itself tells you the magnetic field decay has to play a role. Otherwise, why don't we see many 20, 30, 40 second pulsars? We don't. They're clustered all around here. And theoretically, this is exactly the expectation that it's what the models predict if you have magnetic field decay. So this is how the pure derivative goes if the magnetic field decay, the B field decay. There is some point where the real age becomes very different than what you measure from PP dots. So these are the tracks. It means it's a steady state luminosity. So the outburst will come later. Yes. So this is exactly. So this is the steady state, which is one part of the story. Right. So it's subdominal over. So if we integrate this over the total time scale, it's 10 to the 48. A single event, a single SGR, which is enormous, would have 10 to the 46. The one I showed that was actually the most energetic one. So it is subdominant, and the small bursts are really tiny. It's like 10 to the minus 7 or so. So they don't influence here. So this is basically an indirect, even just this plot, even just this. Just this. It basically provides evidence of the fact that theoretically we predicted that there is here a region where the objects should cluster, and they do cluster here. This also gives us, like some ideas on how actually objects that we, observers have always classified in different ways, how they first detected, but they actually, these objects here might actually be old magnetars. So it's not that necessarily they were born, like these are born as with one label, these are born in another label. It's simply, there is a range of magnetic fields, and some that we observed to be older, they were simply older magnetars. So they're not like necessarily different class. The square under, okay, so the squares are the actual, so they're ages, points. So it was 10 to the, if I try to remember, I think it was 3 times 10 to the 3, 10 to the 4, 5, 5 times 10 to the 5, if I remember correctly, but they're actual ages. Yes. Mm-hmm. Right. 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 So it's a right. So the combination. So after 10 to 4, 10 to 5 years, so there is a combination between the luminosity that get much dimmer here. Right. So this. So there should be. It's a good point, but it is most of this. So something I want to point out. So, most of these objects here are local, because there's NH, the galactic. 10 to the 4, 10 to the 5. Yeah. Yeah, no, right. So okay, so right. So two things. It is a good point, but the number are still low number statistics to. Right, but yeah, no, I think here the main bias is indeed because they are observed all over the galactic planes, So they are the ones that have lower luminosity are actually very close. So an object of with a luminosity of 10 to 32 or so would be very hard to see across the galactic plane. So some of these objects are really across the galactic plane. They have distances. Now, I don't know exactly what the nature would basically make it, but there is around here we start missing a lot of them. As a matter of fact, because these are all really nearby objects, whereas these ones are not. They're distributed throughout the galaxy. So I'm guessing that is the number one. That is reason. The other also I want to mention, ages here are still there are some errors on ages, and in fact, there are errors here in this direction because they are measured based on. So some of these are arrows, point in this direction because they are estimates based on pp dot. So it's a dynamical age, and it's not. It has some. It actually overestimate if anything. So a few of those, but only a few, have an associated supernova remnant, and then from the age of the remnant, which it has its own uncertainty. So the ages have. We try to put error bars as as best, but it's So that's the other thing. So some of those are actually more near. Right, that's a good point. Yes, absolutely, and we will. There will be I'll get to that. We'll get there. So here it's basically. So as we'll see, there is a temperature distribution on the surface of the star, which will become one topic in a few slides 10 slides from now or so. But this is like an integral over. So this is an integral over the old luminosity for the star, but the temperature might not be homogeneous. In fact, as we'll see later, and that's one other prediction that will come. Okay, so I'll try to continuing on. Okay, so with that, those two plots show that overall the bulk properties can be reproduced by modeling. Coupled thermal and magnetic field with the important role of magnetic fields. However, so as we were thinking more about these objects, then I wanted to understand a little bit more detail in further details. So first of all, something that it always puzzled me since the very beginning that I was hearing about these objects, the fact this separation SGR, which were what objects classified as SGR. Typically more active, large flares. Also, they had the property that I happened to read in a paper by Vicky Caspi, where they were saying that the outbursts there in the SGR type are uncorrelated with phase. Actually, Eric and I were discussing some of these things years ago. We're uncorrelated with phase, meaning that pulsation max. So the phase is basically in a pulse profile indicates one location. So they were. Uncorrelated means they basically would occur all over the surface of the star. So there's no correlation whether you're seeing a peak maximum or minimum and whether you see an outburst. These HSP-like objects, on the other hand, have more moderate activity. They don't display flares. And they had this particular property that, again, in the observational papers without any explanation, they were saying, okay, we find this, that the outbursts tend to be more correlated with phase. There was something that was like somehow it remained in my mind as a property. So there was that, but those are more subtle details. What actually was something that really got my attention, which is why I spent the last few years working a lot on this object, was summarized in this plot. So this is now a more updated version. And it actually, it's not even that updated because there is already another object here compared to the plot I showed earlier on. So earlier I was, I showed a plot to show how, okay, the magnetars here, the other objects here, and everything seems to be understood. A few years ago, and there was a paper which shows, no, there's much more to that. So what this plot shows here is with different symbols. These are the standard magnetars that I discussed originally. These are the standard pulsars, rotationally powered. However, observations showed something very puzzling. That is, these low B magnetars, there was outburst activity being seen from objects that had low magnetic field. This actually, it was an error here on this, and now it's a measurement. So it's this object has a field of 6 times into 12 Gauss. Something, it's an object that should completely not behave as a magnetar. And then on the other side of the story, which is somewhat related, but it has the opposite behavior here, is there are these high B radio pulsars. So these are pulsars, these objects here, which have B fields. As you see, this one in particular, it sits together in the middle magnetars. However, it has a behavior which is completely consistent with this radio pulsar population. So it's a radio pulsar. It was named a high B radio pulsar. So there were, all of a sudden, low B magnetars and high B radio pulsars. And the low B magnetars does not have a radio pulsar. Also, now some have been seen to have radio flares concomitant with flares, but they don't have stable radio emission. That's also for the story. So this is basically the place where I became very intrigued, and I wanted to understand more of what is going on, trying to understand more from first principles, how can this be? We thought we understood. The magnetars are high magnetic fields. The magnetic fields are doing everything. The other low B fields, the magnetic field doesn't affect. How can we have this? And in particular, actually, here I point out that there were 2 objects that got my particular attention, which I think there is one is this one, and the other is one that lies on an almost parallel track. So one at the magnetic field, this is a pulsar with 5.7 times 10 to the 13 Gauss, luminosity 10 to the 33 erg per second, so, and behave like a radio pulsar normally. The other is 2259, whatever they have their names. But the point is that the B field is almost identical, luminosity 2 orders of magnitude higher, and frequent outburst. So the big real, and then this low B field object, which is this one here. So it was really, okay, how can we be, how much do we understand about magnetars if we have now these objects that are really mixing things up. This is unabsorbed. It's corrected for absorption. So these are intrinsic, as far as. Yeah, exactly. It's the extra weak. The radio. It's a radio pulsar. So it's behaving like it's a radio emitter. It's just like a quiet radio pulsar. And there it's this one here. So high B is called high B radio pulsar. So this is basically this slide, this figure here with this observation was what triggered a lot of my interest in understanding the whole phenomenon of magnetars. So we were joking with them. Yeah. So it's estimated. So if we don't have other ways, the simplest way is by via PP dot. PP dot, which has it's a few order of magnitude. So if we see, some cases there are cyclotron lines, and then you have to know whether it's electron or proton. So that's if you. So in a few cases there are some lines which they have been debated the lines because also. Detecting a line is not a very easy thing, and it's also the interpretation whether it's an ion line or whether it's So basically that's where it stands. So there is not a really secure. So that's a PP dot. P over P dot. Yeah, it's basically. Yeah, absolutely. Yeah. So that plot you can show it in multiple ways. Exactly, age versus B. You can show it in as you like it, since the two are correlated in dipole model. Okay, so basically, so joking here, trying to understand this whole picture. We talked about having a ground unification where we could we will try to understand all these properties. So first of all, it's not just the luminosity that was part of the story, but also we wanted to understand, the other, why some outbursts, why not, and others not. So what we did is I started to work with those pawns. So we coupled, we introduced in this code also, well, as we were calculating together with the B-field evolution, also following the stresses, and then comparing every moment of the simulation how the magnetic stresses would compare with the breaking stress in the crust, for which there are estimates from molecular dynamics. So we used the estimates, so we did not compute the stresses ourselves, so we used just work from molecular dynamics that yield that's given basically fitting formulas. So that's the for the crust. So the crust is basically the crust is basically just iron metal. So it's a very simple. So it's just ideal equation state. Yeah. So this is because it's just the outer part that we are. So it's iron basically as best as we know. It's high pressure, absolutely. Yeah. So one thing that now becomes very important, while as as a theorist, you can simulate also what you don't measure. Now, observe, that is the cool point here, because what we measure from PP dot is the dipolar component of the magnetic field, but something that could play a role, and that was where we set to explore, which turned out to be major important, is also there could be a strong toroidal field. And in fact, in ideas where magnetars are the result of strong dynamo action early on, you do expect that strong toroidal field. Just naturally how the dynamo by the differential rotation will operate. So that is the clue. So what we did was basically exploring in the simplest possible scenario, where we started with certain magnetic field configuration with different amount of dipolar and toroidal field, and also different strengths of the dipolar field, and see what we predict. One, for the luminosity as a function of time, and second, for the stresses in the neutron star as it ages. So what we have here, so these are 3 snapshots. So this is the crust, which is expanded, I think it was a factor of 6, just for clarity. And the color, it's a color scheme where yellow is made so that the color, wherever it's yellow, it's a place where the magnetic stresses exceed the breaking stress of the crust, the breaking stress. Oh, so that would be in the core. So here the magnetic field is in the crust, right? So we have different magnetic field configuration. This here is one particular case where we have a dipolar field and a toroidal field, which we start. This is also it's a toroidal dipolar field, so it's wrapping all in the same place. So by doing that, we could associate magnetic stresses in different directions with different type of events, different type of what we call. We don't model the outburst, what happens after, but we say, okay, once the crust breaks, then there will be some kind of release of event. So by doing that, we were already start associating certain type of crust yielding with certain frequencies, certain energetics of events. These are snapshots. I'm going to show a movie. Absolutely. Sorry. So these are in radial coordinates in the. So this is in. So it's basically it's okay with. So what I simply indicate here. This is a magnetic stress in the theta phi plane. So theta phi. So this is a really radial coordinate. So theta phi plane would be basically a stress in. So the theta phi would be like in this like this type of stress here. So you have stresses, possible, but as the magnetic field evolves, you can have stress in this direction, this direction, this direction. It's it's basic. Yeah, it's a stress in basically in the three possible situation. Right, and it is. So no phi. Oh, sorry. Maybe no. It's yeah. This is a cut. But this is axisymmetric, yeah. And the dipolar field is vertical, right? So it's B phi. That's exactly. It's B phi B theta. Yeah, that's exactly. Yeah. That's exactly what it is. So yeah, exactly. So what I show you, so these are simply, now there are two movies with two different magnetic field strengths, and they show how, so these are, this is a lower field. Okay, start. This is the age, and every so often, if you see a yellow, it's basically where the neutron star would break. This is a low B field. It was a 10 to the 14 Gauss, no toroidal component, so it stays very asymmetric as we live it. And this is simply just showing the effect, the pure effect of the strength of the magnetic field, and also the comparison between just a sec, finish the sentence between this and the next one, and then also showing the effect with age. As you see, with age things get slower from. So this is just a simple poloidal. Without with no, so that's an all separate story, which is just something we can talk later about that, because it's something we're implementing now, because it would allow us also more to study the coupling with the external and the magnetospheric effects that Liutikov Beloborodov. Yeah, let me not get into that now. And this is same thing. So it's again this is just purely poloidal, nothing else, but stronger by factor 10. So the whole point of this too is showing how the frequency of outbursts with it. So this is the age of star in years. It's going very quickly. And also, so the comparison again is strength between the previous and the second. And here, for a given magnetic field configuration, how things vary with age. So they go slower. So these are again simply two examples. And we ran many simulations. So I'm showing now a few results, trying to then go back to the observations. So first of all, so this is just for, again, one specific configuration here. So it's neither of those ones. So here we had also toroidal component. And what we have, there are three. So after running your simulation, we can characterize the properties. No, the initial number is not a random number. It's just a particular configuration that we choose as we're exploring many configurations. Fitting here is a big word. So we're basically trying to, saying, okay, given a certain magnetic field configuration at birth, and we explore many, what does that gives us in terms of the observational property of an object with these characteristics? So here for this particular configuration, so I'll show you one, and then I'll show you some other result which conglomerate the more initial conditions, so to speak. So here, for example, this is the waiting time. So what this observation, what this theoretical result shows that for an object which is younger, and this is again the eye, just looking at the simulation before kind of gives an idea, the median frequency, the median time between two outbursts is somewhere a few months. As the object ages, you get longer, and then it gets longer and longer. So something that initially we had actually, as we were writing this paper, we were like, okay, these are XPs, these are more like SGR, these are more XPs, and then we realized, no, there is actually, we should stop classifying them as it has been done observationally. These are SGR, these are simply neutron stars. It's basically one class. There is no really, an intrinsic name tag with which they were born, but simply the way they manifest itself is when we detect it, how they were first observed, and a combination of their age and magnetic field strength. So as it ages, it will get older. This again for one particular magnetic field configuration. We also found a bimodal distribution of energy, which is related to the different stresses. This is again not expected. It was, but we see a small burst and giant flares. It wasn't something we were looking for, but it came out. And something else again, they came out because this is the only initial condition. All the rest are just counts. There is no further fiddling. What we found that first of all, what this is the outburst fraction as a function of the angle. So this is the angle is basically the position on the surface of the star. So what we find here is that what are the younger objects, which is the solid line here, they have outbursts distributed somewhat along the whole surface of the star. As the object ages, then the outbursts tend to be focusing more in a region, which we found correlated with the highest temperature of the star. Interesting. These were the properties that in the old Vicky Caspi paper that been in my mind, these were the SGR, more active outbursts distributed on the surface of the star. And the XP, which we call now, I mean, they're XPs, but we simply say these are older objects with generally lower magnetic fields. The outbursts more concentrated, correlated with phase. So it came out naturally out of the simulations. So what we emphasized, from a theoretical point of view, really, there is no separation between what we call SGR, what we call XP. And interestingly enough, now, over the last 3 or 4 years, as more objects are being discovered, actually the old map is filling. So even in the observational paper now, what is XP or SGR is no longer a distinction. And Vicky Casper herself is like, okay, well, this is SGR simply because we discovered it's SGR, or XP could have a giant flare, and then, how do you call it? You initially discovered as XP, but then it's basically simply a result of how we discover, but their properties depend on their internal field. Some. Yeah. So these are simply 3 age cuts. 3 age cuts. So these are sort of arbitrary, what we call a young. So it's somewhat arbitrary. It's just typical ages. You can make it a bit different, just to separate them. So here, because this is one simulation. Okay, well, this comes next. So this is it's a one simulation. So you have one magnetic field at birth, and then and then it evolves. Right. So it's coming in the next slide. Exactly. So we explored, try to understand the old picture. We explored more, which is exactly here. So in particular, let me not go into as much as the energetics since they're more uncertain. But let me go into outbursts. So what we did then, for a given dipolar field, so these are 2 different dipolar fields, what we did running a certain simulation with increasing toroidal field. And what we found is that you can have, again, 2 objects born with, this is outburst per number of years. You can have 2 objects born with the same dipolar field, but one has a much stronger internal toroidal field, which you don't measure, but it can give you much larger outburst rate. And this is the old clue now to see how you can have high B pulsar, and you can have a magnetar which were born, or a magnetar behaving object, which have the same dipolar field, but one behaves like a magnetar because probably we suggest it has a much stronger internal toroidal field that you don't measure in the Pipito diagram. You just see them because you're measuring this, but they can behave very differently. So this is the outburst rate. And then the other piece, which is the luminosity, where again, we ran many simulations, one for initial B field, and this is no toroidal field, so this is just as a function of the dipolar field for different ages. So to 0 toroidal, so the luminosity does depend on the dipolar field if there is no toroidal field. Now, in addition, for a given dipolar field, so here dipolar is fixed, the luminosity will be much higher if there is a strong toroidal field. So once again, now this gives you the other piece, the other missing piece, going back to objects that can look very similar, where one, however, is a much higher luminosity. Remember, 10 to the 35 arc per second versus 10 to the 33, having the same measure dipolar luminosity, dipolar magnetic fields. So it basically, it can all fit together. And here, our general prediction from this for the luminosity of the bulk population with B field, with dipolar B field, is that so there is a correlation with dipolar field as you see here, but there should be a large scatter because of a large variety of internal toroidal field. And I was a couple of years ago, I was giving, I was presenting these results at McGill when they were just, it was funny because they were just observationally, they just made this plot basically where they're looking, they were measuring extra luminosity versus dipolar field. So I could immediately compare. And what you see here is basically the extra luminosity increased with dipolar field, but there is a large scatter, which our simulation, again, predicts exactly this behavior where the large scatter is due to the internal toroidal field. It's not, again, it's tightly correlated with the dipolar because of this other component that we don't measure through dipolar measurement, but we measure through, but we infer it indirectly in the luminosity. I have 5 more minutes. Okay, there have been a lot of questions, so I realized that the time is not usually where I am. So just tell me whenever, because don't want to go over time. So now so one question that obviously then came next, as we were working on this and making these predictions, the question came: can we find a more direct probe of the internal toroidal field? Because these are still indirect. I mean, there is quite a good match with observation. We can explain all these puzzling properties. But however, can we actually have it even a more direct way? And the answer is actually yes. Because for a certain magnetic field configuration in the crust, since the conductivity is highly directional, then that will be reflecting on the temperature distribution on the surface of the star. So this is well-known fact. It's not it's something that we thought of first. But the point is that we can now associate a certain configuration that where we say, okay, this object should behave like a magnetar, and we can predict what type of temperature distribution should have on the surface, like broad properties. So if there is a poloidal field only, these are examples. Again, depending on the field, you get a different thing. But the point is that if there is purely poloidal, it will be symmetric with respect to the 9 degrees. The temperature has a maximum, minimum, maximum. On the other hand, if poloidal plus toroidal field, and this is a toroidal poloidal in this particular configuration, will be asymmetric. So the symmetry gets broken during the evolution, and you end up with configuration. This is again one example. It's not necessarily this one, but it's one typical example of a poloidal plus toroidal configuration. Now, how do we detect directly temperature distribution? We detect them by looking at the pulse profiles, which is something that observers can directly measure. Poloidal field only will give you very nice double-peaked profile. This is 1990, also depends on the geometry. On the other end, the poloidal plus toroidal field can give, this is very lightly colored on here, so I'll put a line here with the pointer. So as you see here, can give a single pulse profile and also a very high pulse fraction. And as we were working on this, for a completely different reason, like trying to test the toroidal field idea, we came up with something that was actually a very pleasant surprise, because for a number of years, this observation had been noticed that most magnetars are single-peaked. So that was like something that had been noticed over and over. And what we found is this is exactly what you expect. If you have a absolutely, 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 this is full, absolutely. So this is full GR. This is with a star of because also it depends on the compactness of the star. So that's why it was such a surprise being able to have such high pulse fraction. So this was a star 11.7 kilometers. So if you make it smaller, it will be, you have a higher suppression. But right, it's because that's exactly a combination of because when you're 99, you see now, then you see, as you're going back, you start seeing more of the other. I mean, when you have only one single region, as you're back, you go to a region where basically the hotter region is completely out of view. So in principle, you could reach even 100% pulsation fraction if you have a very high contrast. So that's the whole point of one hot region versus two hot region. And again, because of the GR effects here, these are further suppressed because you see, you have two hot region, but you see more. I mean, like for a star like this one here, I calculated actually up to a region. It was like, I even remember the number was 120 degrees back, the outermost region for this, as I was just playing before. 5 minutes, okay. The pulses are show. The beginning. So those pulses. So those were within an outburst. So there was magnetospheric. So these are the quiescent passing. Quiescent emission, absolutely. So those were the pulsation during the outburst, which is completely, it's magnetospheric there, so it's much, it's a completely different physics. But this was, again, it was, since it had been a mystery for, or just an observation that people kept on making. And then, actually, the last on this. So then going back again and trying to relate the results from theoretical simulation to what is actually observed. So what we did was trying to to simulate as close as possible the observation. So basically, what do observers do? So these spectra usually don't have a super high resolution. So they typically will fit with a single black body. Most of them typically are. I mean, they are multicolor black body, obviously, because of the temperature distribution on the surface of the star, but they're typically will fit with that. And many of these neutron stars, I was saying early on, are also, they have very high absorption. Now, so what we did was basically we took our temperature, theoretical predicted temperature profile. We generated relativistic spectra with all the GR effects. And then we import into XSpec this fitting code, ran it as if it was a fake spectra, so generate a spectra from that, and then fit it with a black body as an observer would do. And this is what we found. And we did that for both a dipolar component only and a dipolar plus strong toroid as a function of also the absorption, because in some of these objects, the absorption is very high. It's like 10 to 22 particles per centimeter squared. So it's a particularly important. So, and what we found, it was actually, again, very interesting in the context of actually fit the observation. So for the polar field, what we found is the temperature, since basically the temperature we were inferring from the black body was not too different from the, this is the range of temperatures of the simulation. And it was not very dependent on NH. This is, again, because there is not a huge gradient. Now, in the strong toroidal component, on the other hand, strong toroidal component, where there was one outer region and the rest of the star was cooler, then what happens is you're increasing NH, then you're hiding more and more of the cooler region, and you're inferring, as you're fitting with the black body later, you're inferring a hotter and hotter region, even if your actual temperature is lower. I mean, it varies between a maximum and minimum because it's, hours, so it's realistically determined, like realistically produced. This is phase average, yeah, absolutely. So phase result. So we didn't do. I mean, we can do it, numerical. We can do phase result. We didn't do it particularly here because we were showing the point of the radius, which is we were basically trying to do things as observers do. So for single object, now we have actually, since you mentioned. We're actually just modeling right now SGR, the low B ones, where we have somewhat phase resolved observation, so we're doing that. But this is, here we did it just to make the connection to what observers do. They fit with the black body to the phase average. They find certain, they were finding small radii, which was, the typical, originally a puzzle. Actually, even when I started to work with this, I had a paper try to explain this puzzle, as a result of atmospheres and other things, because people didn't believe that an object with, strong magnetic field should be emitting from the Earth's surface. Nobody could understand why we could have small radii. So I was having a paper, tried to, go around this problem, so to speak, which now is basically comes naturally. So here, if you are fitting with the higher temperatures, and then you're fitting to you have a certain flux. And then, correspondingly, the radius there, if your temperature is higher than your actual temperature, correspondingly, you infer a region that's smaller when you do a fit. That's like the way, these fits are done. So basically, what we found, again, this is a completely independent evidence. The neutron star with a strong toroidal field here. This was the number. Seen through high absorption can have black body radii as small as 1 or 2 kilometers, which is, once again, typical of magnetars. So it all fits together, and the axion part of cosmology will not fit in the talk. But there were many questions. I will. So I guess the summary will just stop to so. They were starting to put together the various pieces of this mosaic, making up high magnetized neutron stars. So the whole phenomenology fits together, and more work on tighten up details now. It's still ongoing, and next there will be some other time. I will return. Okay, let's stop here. It's already a little time.